Welcome, my dear learners, for this course on tribology. So far, we have discussed the concept of lightly loaded bearings and also we have solved numerical problems on lightly loaded bearings. From today's lecture, we are beginning a new topic, that is idealized full journal bearing. Let us conduct analysis of idealized full journal bearing in today's lecture. Moving for today's topic, that is idealized full journal bearing. As we already discussed, if a bearing is loaded with a very small weight and the viscosity of the lubrication oil is very high, and if the journal rotates at very high speed, then the eccentricity between the bearing and the journal can be neglected. Such bearings are termed as lightly loaded bearings. But in practice, the eccentricity cannot be neglected. There will be an eccentricity between the center of the bearing and center of journal. The journal rotates with some amount of eccentricity. How to solve such real case problems can be addressed through the analysis of idealized full journal bearing. Now, in order to understand the analysis of idealized full journal bearing, let us derive expression for fluid film thickness at any given angle in the journal bearing, and also let us derive expression for pressure distribution, load carrying capacity, frictional force, and understand what is Sommerfield number in today's lecture. If I consider a full journal bearing, let us consider a journal running with eccentricity inside a bearing like this. Let O be the center of bearing and O dash be the center of journal. So this is bearing and this is journal. Let us take this as the axis X. Let us take this as axis X, and it is acted upon by load W. Now let us consider an element at an angle of phi. Let us consider an element at an angle of phi like this. And let us take this point as A and this point as B. Now let us connect point B to O dash. Point B to O dash. Let the angle made by line B O dash with reference to axis X be beta. Let us call this angle as beta, and let us call this angle as delta for analysis. And we have minimum film thickness here. So at this position we have minimum fluid film thickness. This is H minimum. We are considering the journal rotating in counterclockwise direction. The journal rotates in counterclockwise direction with eccentricity O dash, because this is the center of bearing and this is the center of journal. The distance between the center of bearing and center of journal is termed as eccentricity. Now for analysis, to derive expression for fluid film thickness at any given position phi on this journal bearing, let us consider the radius of the journal as, we have radius of journal. Radius of journal, which is denoted by small r, can be written as O dash B. O dash to B is the radius of journal, right? So similarly, radius of bearing, radius of bearing, capital R, can be written as OA. O to A is the radius of bearing. Now I can write the film thickness H as film thickness H. Film thickness H can be written as radius of the bearing OA minus OB. OA minus OB. So we have OA as radius of the bearing. If we subtract OB from that, I will get what is the film thickness. Right. So therefore, to determine the film thickness, I have this equation. Let us take this equation as equation number 1. So now I should determine what is the value of OB. Now if I find what is the value of OB, I can derive expression for fluid film thickness. I want to determine the expression for fluid film thickness in terms of phi. Now in order to do so, let us consider the triangles like this. We have axis X moving like this, and we have line AB starting from center of the bearing like this. We have line AB. At point B, we have one more line, that is O dash B. O dash B. Now I will take this point B to this point as H. O. So this angle is already known to us. This is A and this angle is phi. Correct? This angle is phi. Whereas this angle is also known to us. This angle is taken as beta. Right? So this angle is taken as phi and this angle is taken as beta. Now I can approximate this as a triangle because I am considering a small element. So therefore I can approximate it as a triangle. So I have two triangles, namely OBH and O dash BH. So use these two triangles and find what is the length OB. So if I know the length OB, I can find what is the fluid film thickness and express this OB in terms of phi. Now from triangle OBH, that is from triangle OBH, I can write the value of sin phi as sin phi can be written as opposite side by hypotenuse, that is BH divided by OB. So because we have right angle here, hence I can write OB, or getting the common side BH. For both the triangles BH is common, so therefore expressing for BH, I will get BH as OB sin phi. OB sin phi, take it as equation number 2. Now from another triangle, what we have, that is from triangle O dash BH. From the second triangle O dash BH, I can write sin beta as sin beta is equal to BH divided by O dash B. BH divided by O dash B. So therefore what is the value of BH? BH will be equal to O dash B times sin beta. Take it as equation 3. Now compare equation 2 and equation 3 and equate for side BH. If I equate equation 2 and equation 3, I can get what is the value of OB. So therefore equating equation 2 and equation 3, if I equate equation 2 and equation 3 and resolving for OB, I will get OB sin phi is equal to O dash B sin beta. What is the value of O dash B? O dash B is nothing but radius of the journal, that is small r. So hence the side OB is equal to small r times sin beta by sin phi. Sin beta by sin phi. But I want fluid film thickness in terms of phi alone. Therefore I want to eliminate beta. I don't want to have beta. At any given position phi, I should tell what is the fluid film thickness. So therefore I want to eliminate the angle beta now. Now to eliminate the angle beta, so from the same triangle OA, and let us call this point as M, this as H. Now for analysis we have considered OBH and O dash BH. Now from triangle OAM, what I can write from triangle OAM, that is, let us call this as figure B. So using figure B I resolved. Let us call the original figure as figure A. Now let us formulate one more triangle, that is, we have line like this at an angle of phi. We have taken some element from the center of the bearing O. Let us call this as A and this as M, and we have point B joining to O dash. Now what I will do, I will draw a line parallel to this here. I will draw a parallel line to this here. That is, I will draw a parallel line like this, which is parallel to O dash B. So this line and this line are parallel to each other. O dash B and this new line are parallel to each other. If I do so, what I will get? So this angle is known. This angle is already known for us. So therefore this angle must be the same. Right? So these two angles are nothing but delta. Now this angle is known, that is beta. Therefore this angle must be beta. Right? If I draw a parallel line here, shift this parallel line here, so these two will become alternate angles. So therefore delta and this must be equal to delta. And this overall angle is known, that is phi. So this angle is nothing but delta, because we have drawn a line parallel to O dash B like this. So this overall angle is also known, that is phi. So therefore what I can write from figure C, I can conclude that phi is nothing but beta plus delta. Phi is nothing but beta plus delta. Hence beta can be written as phi minus delta. Hence beta can be written as phi minus delta. Let us use this equation here in equation 4. So therefore from equation 4, what I will get the value of OB as, OB is equal to R sin of phi minus delta divided by sin phi. So this is of the form sin of A minus B. Expand it using the formula sin of A minus B. You will get OB is equal to R of sin A cos B minus cos A sin B, whole thing divided by sin phi. Now I will divide the sin phi individually and simplify. I will get OB as R into cos delta minus cos phi sin delta by sin phi. cos phi. Here I should write cos phi. Correct? So I divided sin phi individually. Let me write it properly. This is cos delta. Cos delta minus cos phi sin delta by sin phi times r is the value of OB. That is by substituting beta is equal to phi minus delta. Now I want to know what is the value of delta, sin delta and phi. So therefore I want to express this in terms of phi. So therefore if I find out what is the value of cos delta and sin delta, that is more than enough, right? Hence now I'll have one more construction to find the value of sin delta and cos delta. That is, I'll take one more figure from here. We have center of bearing as O and journal as O dash, and we have a line like this, which is nothing but BO, which is joining for O dash. Now what I will do, I'll extend the line BO further. I'll extend the line BO further. I'll extend the line BO further like this, and I'll drop a perpendicular from here to this, like this. I'll drop a perpendicular and call this as K. Since this angle is already known for us, this angle is phi, and this is the opposite angle, this angle must be equal to phi. And this angle is already known for us. How much is this angle? Yes, you are correct, it is delta. Now we have two triangles, that is O dash BO and one more triangle O dash BK. So from triangle, let us call this as figure number D. Figure D. We have two triangles O dash BO and O dash BK. So from triangle O dash OK and triangle O dash BK. I know the angle at O, I know the angle at B. So from triangle O dash BK, from triangle O dash BK and triangle O dash OK, what I can write for sin phi and sin delta? From the first triangle O dash OK, I can write sin phi as opposite side is O dash K divided by adjacent hypotenuse. Hypotenuse is nothing but opposite side for 90 degree, that is O dash O. Similarly from triangle O dash BK, I can write sin delta as, sin delta can be written as opposite side by hypotenuse, that is O dash K by O dash B. O dash K by O dash B. So I can resolve for side O dash K. So from here I can write O dash K as O dash O sin phi. From here I can write O dash K as O dash B sin delta. Correct? Now I can equate for O dash K as, we know O dash O is what? Eccentricity. What is O dash B? O dash B is nothing but radius of the journal, R. So therefore equating for O dash K, I can write it as O dash O sin phi must be equal to O dash B sin delta. So therefore what is the value of sin delta? Sin delta is equal to O dash B is radius, O dash O is eccentricity times sin phi. So I have eliminated sin delta. So sin delta is eliminated because I have expressed sine delta in terms of radius of journal, eccentricity and phi. Now use this to find the value of cos delta. What is the value of cos delta? So cos delta can be written as what? Cos delta can be written as root of 1 minus sine square delta. Root of 1 minus sine square delta. Because sine square theta plus cos square theta is unity. Hence cos theta can be written as root of 1 minus sine square theta. Now we know what is the value of sine delta. If I substitute and solve, I will get cos delta is equal to root of 1 minus r by e whole square sine square phi. So sine delta is equal to O sin phi by O dash b. So it should be E by R. Sorry, it should be E by R. Kindly make a note. It should be E by R. E sin phi by R. So it is E square by R square. E square by R square. So that is cos delta can be written as root of R square minus E square sin square phi divided by R square. Now if you observe, the eccentricity is very small compared to the radius. So therefore we can neglect eccentricity in comparison with radius. So since eccentricity is very small compared to radius, neglect eccentricity. Put E is equal to 0, hence I will end up with cos delta as 1. That is r square by root of r square by r square. Root of r square by r square is unity. That is cos delta is equal to root of r square by r square. This is what we will get. So we got the value of sin delta. We found that cos delta is equal to 1 based on our approximation that eccentricity is very small compared to radius of the journal. Now make substitution for cos delta and sin delta in equation number 5. So therefore from equation 5, OB will become R times 1 minus cos phi. Sin delta is E by R sin phi. So sin phi and sin phi will get cancelled. I left it with E by R cos phi. E by R cos phi. Therefore OB is R minus E cos phi. So we have calculated what is the value of OB in equation number 6. So now put it in equation 1. You can see that if you people tell me the value of phi, I can tell what is the film thickness by knowing radius of the journal, radius of the bearing and eccentricity. So therefore from equation 1 we have found out film thickness H as, from equation 1 film thickness H can be written as capital R minus small r plus E cos phi So capital R minus small r is nothing but radial clearance plus E cos phi. The difference of radius of the bearing and radius of the journal is called as radial clearance, whereas diameter of the bearing minus diameter of the journal is called as diametrial clearance. Now if I take the radial clearance common, I can write it as CR times 1 plus E divided by CR cos phi. What is CR? CR is radial clearance. What is the relationship between radial clearance and diametrical clearance? Radial clearance is half of diametrical clearance. So therefore, CR can be written as C by 2, where C is diametrical clearance. Hence, diametrical clearance, if I introduce, it is C by 2 times 1 plus 2E by C cos phi. Now, you know that 2E by C is nothing but epsilon, that is eccentricity ratio or attitude. So, substituting which, I will get film thickness H has diametrical clearance by 2 times 1 plus eccentricity ratio or attitude into cos phi. So this is the expression for film thickness, fluid film thickness or lubricant film thickness at any given position phi. So this is given by equation, this is nothing but equation 24.31 referring to page 24.13. So this equation for minimum oil film thickness is given by equation 24.31 referring to the design data handbook written by K. Lingayya. We are referring volume 2, 8th edition, chapter number 24. So you can verify the equation what we have derived. So this is the expression for this is the expression for fluid film thickness. Let me pause this video for a while so that you people can copy it down. Later we will continue to determine the Sommerfield number or bearing characteristic number. So we have derived expression for fluid film thickness H in terms of attitude or eccentricity ratio and angle phi, and also I require diametrical clearance. Now moving ahead, let us derive expression for pressure distribution at any given angle phi. So now to derive expression for pressure distribution, we should recollect, that is our second topic is expression for pressure distribution. Expression for pressure distribution. In order to derive expression for pressure distribution, let us recall Reynolds equation in 2 dimension. So we know that Reynolds equation in 2 dimension is given by d by dx of h cube dp by dx is equal to 6 eta u dh by dx. So this you people already know, this is Reynolds equation in 2 dimension. Now let us express dx in terms of d phi, for which I will take an element x from the journal like this, O dash b, let us take an element x at radius r at an angle of phi. At an angle of phi, let us take an element of the journal like this, let us call this as x, on which we have pressure acting P. So I taken a small element dx at a distance r at an angle of phi from the journal. So I can write x as r phi, therefore dx can be written as r d phi. From arc of a circle formula s is equal to r theta, I can write x as r phi, so therefore dx as r d phi, because r is constant radius, whereas phi is variable, it varies from 0 to 360 degree. Now replace x by r d phi and solve for pressure P. So if I do that, what I will get, I can write this as d by r d phi times h cube dp by r d phi is equal to 6 theta u dh by r d phi. We'll cancel off radius on both sides. Now I left out with, I can take this 1 by r and take it to right hand side. So I'll take 1 by r out and taking to right hand side, it will become 6 eta u r, that is d by d phi times h cube dp by d phi is equal to 6 eta u r dh by d phi. Correct? I have taken this r outside and send it to right hand side. Now if I integrate this equation, I will get, if I integrate this, differentiation and integration will get cancelled. I left out with h cube dp by d phi plus constant c1. Because it is indefinite integral, this must be equal to 6 theta u r h plus c2, constant of integration c2. So if I integrate, the differentiation and integration will get cancelled. Here the differentiation and integration will get cancelled. Here also I don't have a limit, here also I don't have a limit, therefore I have added constant of integration. Now I can write it as h cube dp by d phi is equal to 6 eta u rh minus c1 minus c2. I have taken this constant of integration to right hand side and simplified. Now further I can simplify this as h cube dp by d phi is equal to 6 eta u r. I will take 6 eta u r common. If I do that, I left out with h minus c1 minus c2 divided by 6 eta u r. Correct? Now I divide this h cube. So if I divide with h cube, I will get dp by d phi as dp by d phi will be equal to 6 eta u r into h by h cube minus, let's take this value as a constant k by h cube. Let constant k be equal to constant of integration c1 minus c2 divided by 6 eta u r. Let's take the value c1 minus c2 by 6 eta u r as a constant k and divide by h cube. Now what is this k? That k is nothing but dp by d phi is equal to 6 eta u r times 1 by h square minus k by h cube. A careful observation reveals that if dp by d phi is equal to 0, then pressure will be either maxima or minima. For a function to be maximum or minimum, its first derivative should be equal to 0. If its second derivative is negative, then the point yields as maxima. If the second derivative of this function is positive, then the point yields as minima. Right? So therefore, if dP by d phi is equal to 0 is nothing but condition for maximum pressure or minimum pressure. So if I do that, dP by dx or dP by d phi is equal to 0 is a point where pressure is maxima or minima, which yields us K is equal to H. K is equal to H means what? K means film thickness where pressure is maximum or minimum. K means film thickness where pressure is maximum or minimum. So let's continue further. That is, we have got dP by d phi is equal to 6 eta ur times 1 by h square minus k by h cube. Now I want to find the value of pressure P. So therefore I left out with P is equal to, that is dP is equal to 6 eta ur times d phi divided by h square. What is the value of h? H is c by 2 times 1 plus epsilon cos phi. So it will become c square by 4 whole square minus k d phi by h cube. H cube will become c cube by 8 times 1 plus epsilon cos phi whole cube. Right? So if I simplify further, I left out with pressure P can be written as, let me take c square by 4 common, I left out with 24 eta ur by c square times integral of d phi by 1 plus epsilon cos phi whole square minus, I'll get as 2k by c d phi by 1 plus epsilon cos phi whole cube. So this is general expression for pressure. So if we integrate this with the limits, I will get the solution. Now if we carefully observe, pressure at angle phi is equal to 0 should be equal to pressure at angle phi is equal to 360 degree, because angle 0 as well as angle 360 degree are same. So if this is the angle 0, then that will be the angle 360 degree, right? So pressure at angle 0 and pressure at angle 360 degree are one and the same. So if I use that condition, I will get the equation for K, that is pressure P at phi is equal to 0 must be equal to pressure P when phi is equal to 360 degree, right? Pressure at a point is constant. Now if I do that, what I will get? Pressure at angle phi is equal to 0 minus pressure at angle phi is equal to 2 phi will yield us 0, because they are same, right? So therefore if I substitute the general expression for pressure and solve, I will get it as (24 eta ur by c square times Integral is from 0 to 2 pi d phi divided by 1 plus epsilon cos phi whole square minus 2k by c. Integral is from 0 to 2 pi d phi divided by 1 plus epsilon cos phi whole cube must be equal to 0. So this is what I will get. So sending this to RHS, I left out with 2k by c as, or I will get the value of k as c by 2 times integral is from 0 to 2 pi d phi divided by 1 plus epsilon cos phi whole square divided by integral is from 0 to 2 pi d phi divided by 1 plus epsilon cos phi whole cube. So if I solve further, I will get the value of k, that is k is nothing but film thickness where pressure is maximum or minimum, as we have from data handbook. It is given as 2c times 1 minus epsilon whole square divided by 2 plus epsilon square. So this is the value of k. K is called as film thickness where pressure is maximum or minimum. Now use the value of k and substitute here, and integrating and simplifying, I will get the expression for pressure. Let me pause this video for a while so that you people can copy it down. Later I will substitute the value of k and give you the equation for resultant pressure. Now moving ahead, so if I substitute the value of k, that is the film thickness where pressure is maxima or minima, which is given by equation 24.35 of our data handbook written by K. Lingaya. We are referring volume 2, 8th edition, chapter number 24. So if I substitute and simplify, that is P is equal to 24 eta ur by c square times integral of d phi divided by 1 plus eccentricity ratio cos phi whole square minus 2k by c, that is 2 by c into k is 2c of 1 plus epsilon 1 minus epsilon whole square divided by 2 plus epsilon square into integral is from d phi 1 plus epsilon cos phi whole cube. Performing the integration and simplifying, we will end up with equation for pressure as P phi is equal to P naught plus 12 eta u divided by xi square d times epsilon times 2 plus epsilon cos theta times sin theta divided by 2 plus epsilon whole square into 1 plus epsilon cos phi whole square. This is phi. So if you integrate and applying the boundary conditions and finding the constants and simplify, you will get this expression where P naught is the pressure at inlet oil hole. So P naught is nothing but what? Inlet oil hole pressure. Inlet oil hole pressure. So therefore the resultant pressure PR, which is nothing but pressure at any angle phi minus P naught, that is P resultant, is given by 12 eta u divided by xi square d times epsilon times 2 plus epsilon cos phi into sin phi divided by 2 plus epsilon whole square into 1 plus epsilon cos phi whole square. So this is the equation for resultant pressure, which is given by equation 24.36 referring to page 24.15 of our design data handbook. Next we have load carrying capacity, Sommerfield number and frictional force. Apart from this, we people should know load carrying capacity. Third one is load carrying capacity. Load carrying capacity is nothing but load corresponding to minimum fluid film thickness. Load carrying capacity is defined as load corresponds to minimum fluid film thickness. So expression for load carrying capacity is given by load carrying capacity, that is W is equal to eta UL divided by xi square times 12 pi epsilon divided by 2 plus epsilon whole square into root of 1 minus epsilon square. So this is equation 24.38 referring to page 24.15. So kindly make a correction. In your data handbook he has written it as 2 pi epsilon. That is wrong. It should be 12 pi epsilon, and here it is written as 2 minus epsilon square. Change it to 1 minus epsilon square. So make these two corrections in our data handbook. So this is the expression for load carrying capacity. That is the load corresponds to minimum fluid film thickness. Apart from this, we should know Sommerfield number. Sommerfield number is obtained by substituting. W is already known. For us, W is pressure times length into diameter, that is pressure times projected area, and U can be written as pi d n dash. N dash stands for revolutions per second. If I make these two substitution for load carrying capacity and simplify, so I will get PLD is equal to eta pi d n dash by xi square times 12 pi epsilon divided by 2 plus epsilon whole square into root of 1 minus epsilon square. So if you simplify, you will get the equation as into L. So LD will get cancelled. You left out with 2 plus epsilon whole square into root of 1 minus epsilon square by 12 pi epsilon, and here I left out with eta n dash by p into 1 by xi square. Here it is 12 pi square. So this is the expression for Sommerfield number or bearing characteristic number. P eta n dash by p into 1 by xi square. Pi square will come here, rearranging the term I will get this. So this is called as Sommerfield number S, and this is given by equation equation 24.39 and equation 24.41 of our data handbook. So this is the expression for Sommerfield number which we will be using. And finally, coming for frictional force, we have friction force, which is given by F mu, which is given by equation 24.43 and 24.44 in referring to page number 24.17. Take out page number 24.17. Here the equations as 4 pi eta ul divided by xi times 1 plus 2 epsilon square divided by 2 plus epsilon square into root of 1 minus epsilon square, and also F mu is given by 4 pi square eta n dash LD times 1 plus 2 epsilon square divided by xi into 2 plus epsilon square into root of 1 minus epsilon square. So this is nothing but equation 24.43 and 24.44 referring to page 24.17. So these are the expressions which we will be using to solve problems on idealized full journal bearing. And for lightly loaded bearing, eccentricity is 0. If eccentricity is 0, attitude or eccentricity ratio will become 0. So if you substitute epsilon is equal to 0, you get the expression for F mu for lightly loaded bearings. For lightly loaded bearings, bearing, eccentricity is 0, therefore eccentricity ratio will become 0. Put eccentricity ratio as 0, and if you simplify, you will get the equation for frictional force for lightly loaded bearings. So these are the expressions one should know to solve problems on idealized full journal bearing. In our next lecture, I will explain what is the significance of Sommerfield number. Later I will take numerical problems on idealized journal bearing. So this completes our discussion on analysis of idealized full journal bearing. That's all from this lecture. Thank you all.